The landscape of Joshua Tree National Park featured in this photo is characterized by unique rock formations, plants, and animals in a dry, arid environment where the Mojave and Colorado deserts meet in Southern California. The area has been inhabited by humans for at least 10,000 years. Late 1920s development of new roads in the area brought developers, gold miners, and poachers of cactus, such as the silver cholla bloom cactus photographed by the NPS, out to the desert landscape. Currently, 591,624 acres within the park are designated as wilderness as shown in the map provided by the National Park Service. Joshua Tree's history as a national park began when a local concerned about cactus poaching made efforts to protect the area and raise awareness, leading to the establishment of Joshua Tree National Monument in 1936. In 1940, the monument's size was reduced, and in 1950, the Oasis of Mara, pictured here, was deeded to the NPS. On October 31st, 1994, Joshua Tree became a national park under the Desert Protection Bill after citizen activists advocated for desert parks and wilderness preservation. This bill drew a new boundary that followed natural features instead of survey lines, providing better resource protection and easier boundary identification, monitoring, and habitat for bighorn sheep. The recorded geologic history of the region starts approximately 2 billion years ago as eroded sediments in the ocean were compressed and fused into sedimentary rock. During the Proterozoic eon, mountain chains rose and the sedimentary rocks were metamorphosed into gneiss, captured by Samantha Larman. The oldest rock found in Joshua Tree dated to approximately 1.7 billion years old. There is also dolomite, granodiorite, and quartzite found in the park. During the late Paleozoic to early Mesozoic, additional offshore sediments accumulated. When Pangaea broke apart, North America drifted west and later collided with the Farallon Plate, forming a subduction zone and pushing Joshua Tree up above water. As North America continued to drift west, it overrode the eastern edge of the Pacific Plate and formed a transformed boundary. Granitic rocks, such as igneous quartz monzonite, make up a majority of the rock formations at the park. Basalt is evidence of past volcanism related to tectonic activity, with many eruptions during the Mesozoic. Inselbergs formed from batholiths and mantle xenoliths that erupted from 50 to 30 miles deep are evidence of igneous intrusions. The bedrock geology of the park is made up of crystalline, igneous, and metamorphic rocks of varying ages, with sedimentary units limited to the past 10 million years. Convergent boundaries are the main force that created the granitic rocks found, as subduction created magma that cooled within the continental crust into intrusive igneous rock. The transformed boundary of the San Andreas Fault, shown in the map provided by the NBS, is one of the forces that drives these rocks back up to the surface. Orogeni's evidence are the Laramide, Nevadan, and Sonomian. The landscape of the Mojave and Colorado deserts is a result of a rain shadow effect as the tall mountains to the west of the region block rainfall, leading to less precipitation in the area. Structural and erosional valleys form along faults in the park influenced by erosion of rock caused by water or wind. Elevations within the park range from 536 feet to 5,814 feet at Quail Mountain. The park is characterized by its sand dunes, dry lakes, flat valleys, rugged mountains, granitic monoliths, and oases. Mechanical weathering creates joints in the rocks that are chemically weathered through hydrolysis and lead to the spheroidal weathering of rocks, creating inselbergs and boulder piles. The tectonic uplift at the San Andreas Fault's Big Bend creates many faults within the park, such as the Blue Cut Fault, which created a pull-apart basin in Pleasant Valley. Skull Rock is an example of rock that has been weathered and then eroded to expose the shapes we see today. Other developments we see are pediments, bajadas, playas, arroyos, and alluvial fans. The best preserved fossils in Joshua Tree come from the Pleistocene epoch, when the area was wetter and cooler, supporting a variety of different animals and plants that differ greatly from what we see today in its dry, arid, and desert environment. It is hypothesized that animals such as mammoths, saber-toothed cats, and llamas may have once populated the Joshua Tree region, evidenced by findings such as the excavated llama foot shown in this photo. During the Holocene epoch to the North American ice sheet began to disappear and the region developed into a warmer and drier climate. Numerous earthquakes have affected the area of Joshua Tree due to its close proximity to the San Andreas Fault system, with one of the more notable being the Joshua Tree quake of 1992. The area is also subject to flash flooding and wildfires, such as the large dome fire pictured here. The effects of wildfires in the area of Joshua Tree National Park are leading to a reduction of habitat loss for plants and animals, including the Joshua tree, a type of yucca, suffering a 90% habitat loss. Recent warming and drying of the area, influenced by the natural processes of tectonic uplift and being in an interglacial period, combined with human-induced global warming, means that the area will continue to see less vegetation and thinner soil. And with less vegetation, there is increased erosion that exposes inselbergs and boulder piles, also influencing the formation of pediments and alluvial fans in the park. Joshua Tree National Park is a unique desert environment that preserves 2 billion years of Earth's history, also supporting a variety of animal and plant life within its boundaries. The Pinto Gneiss and other rocks found in the park are evidence of the tectonic processes that had to occur to form the landscape we see today. By continuing to study the park, we can understand how the area is becoming drier over time due to natural and human forces.